So now we'll look at multiple qubit gates. And so the idea is the same as it was in the single qubit state. So this will be a unitary linear transformation. Okay, so any unitary linear transformation over the complex space of the appropriate dimension will be a valid multiple qubit gates. And so then for 2 qubit states, and our gate G would be a transformation, so a unitary transformation from 4-dimensional complex space to 4-dimensional complex space, right? Because remember, there were 4 computational basis vectors. So the sort of archetype of this is what's known as the controlled NOT gates. Which is C0 for short. And so the idea is that the first bit will be a control bit. Okay, and so that's going to be unchanged. Okay, so this will be unaffected by the transformation. And so then the second bit will be flipped depending on whether or not the control bit is activated. Okay, so if the control bit is 0, then nothing happens. Alone. The first bit is 0, but then it'll be flipped if the first bit is 1. Okay. All right, and so this should kind of look a lot like the reversible XOR that we talked about when we were looking at the classical gates, right? So we said, well, if we do this XOR XOR gate, we can't recover the original input bits, right? Unless we put a bit that's sort of keeping track of what one of the original bits was. And this is essentially what we're doing, right? Because the control bit isn't changed, right? So the first output bit is just keeping track of what the original input bits was, and then the second output bit is containing the result of the XOR. Right? Because flipping, leaving it float if it's 0 and flipping it if it's 1 is the same as XORing those 2 bits. Okay. All right. But again, we're only allowed these unitary linear transformations. So essentially, what we're doing here is we're specifying the effect on the computational basis. And so then what we want to do is write this as a matrix and see whether we really do get a unitary matrix. Okay. Right, so the effects on computational basis vectors is to leave 0, 0 alone. Because if the first bit is 0, then the second bit is left alone. So we would also leave 0, 1 alone. But then 1, 0, so that would flip that second bit, and then 1, 1 would also flip that second bit. Good. All right, so then as a matrix, okay, so remember the idea for these 2 qubit systems is that we can think of them as 4D vectors, right? And so the first component is giving me the coefficient on 0, 0. Etc. Okay. So as a matrix, so U sub Cn. Okay, so this will be a 4x4 matrix. Okay. All right, and so again, since the first component, right, is telling me the coefficient on 0, 0. So I'll basically just want to make the effect of the matrix match up with the effect on the basis vectors. Okay, so basis vector 0, 0 is being left alone. Okay, so essentially the column should contain the vector representation of that computational basis vector. Same thing with the second computational basis vector. And then these two have to be flipped. Okay, so essentially then the way I do that is I was doing this. So my input was 1, 0. I'd be picking out the third column, which would be sending it to 1, 1. My input was 1, 1. I'd be picking out the fourth column, which would be sending it to 1, 0. Okay. And again, we can see this is a unitary matrix because the columns are just the standard basis vectors for R4, and therefore they do form an orthonormal set. Okay. All right. So I can also draw a schematic for this gate. And so the idea is, okay, so this is sort of representing my XOR gate. Okay, and so if I have an input here that's A, and an input here that's B, okay, so a dot in one of these circles always indicates control. Okay, so this is saying activate this gate if and only if the bits along this, or qubit along this wire is 0. Okay, and then this is saying what operation should be activated. Okay, and so that's the XORing of the two input bits. Okay, and so for example, let's look what would happen if we do C naught on over the Bell states. Okay, so 1 over root 2, 0, 0 plus 1 over root 2, 1, 1. Okay. All right, well, again, you could just sort of distribute the effect on each of those basis vectors. Okay, so 0, 0 is left alone. Okay, so that's 1 over root 2, 0, 0. Okay, and then here, well, I have a 1 here, so that would be flipped, so 1 over root 2, 1, 0.